Welcome to the course on Introduction to Electrical Engineering, level lecture 38, today on synchronous machine part 1. So, with the outline of presentation, we will be introducing this machine and then we will talk about applications, then classification and construction features, operating principle, equivalent circuit of cylindrical synchronous machine, then a steady state power angle characteristic, followed by exercise numerical problem and references like. So, starting with the introduction, basic of this AC motors. Traditionally, AC motors may be classified in two broad categories as synchronous and asynchronous motor, and synchronous motor always run at synchronous speed, whereas the asynchronous motor known as induction motor never run at synchronous speed. So, synchronous speed is given by Ns equal to 120 F by P, where F is the supply frequency and in hertz and P the number of poles in the motor or in the machine like. So, normally the AC motors have polyphase distributed winding on stator with equal number of poles on the edge on the rotor, and synchronous machines are AC machines having the field circuit excited by external DC source and the armature circuit with 3-phase balance windings excited by an AC source, and armature circuit forms the stator of the synchronous machine and the field circuit constitute the rotor of the machine. And typical example are here you can see the stator how it is wound with the winding similar to what we discussed last time in induction machine. So, it is a polyphase distributed winding, and normally we prefer to have 3-phase distributed winding apart exceptional cases. So, those 3-phase winding as you can see how it is wound in the 2 ways and you have a 3-phase output, and it is the you have seen how 3-phase waveforms are there of 3-phase output like also. So, now however, for low power synchronous machine the arrangement similar to DC machine can also be used with the field on the stator side and the armature on the rotor side. And synchronous motor the basic magnetic field is obtained by direct current excitation rather than through the air gap from the armature, and in case of the induction motor. So, synchronous motor can be applied or can be used to any load which can be successfully driven by NEMA design B squirrel cage induction motor. However, there are certain types of load for which synchronous motor is especially well suited. It can operate at either leading unity or in rare cases on lagging power factor, providing the function of synchronous condenser for power factor correction. So, of course, this machine can work as a generator also. So, synchronous generators or it also called alternators, as it produce the AC alternating current output, are used to convert mechanical power derived from steam, gas or hydraulic turbine to AC power, and synchronous generator are the primary source of electrical energy we consume today, and large AC power network rely almost exclusively on synchronous generator, and synchronous motor are built in large unit compared to induction motor. Induction motor are cheaper for small rating and are used for the constant speed industrial drive. And typical example, if you see the photograph here, generator for turbo generator driven by steam turbine used in thermal power plant, how they look like. Then generator for cell and pole used in hydropower plant, as you can see here. Of course, they are in large size. So, you can see what is the size typically in light of the the persons standing around it. So, why synchronous machine? It give you high efficiency. So, synchronous motor can be designed to actively operate over the wide range of speed to provide the best drive for a wide variety of load, and of course, it can provide the power factor correction, it can operate a leading power factor, and of course, require the reduced maintenance. Well, it give constant speed means better quality product, and adjustable speed means by lower power cost, and it give a space savings. So, engine type synchronous motor can be connected directly to the shaft and bearing of the driven equipment. Synchronous motor are usually used in large sizes because small sizes they are costlier compared to the induction machine, and the principal advantage of using this synchronous machine are as follows. Power factor of the synchronous machine can be controlled very easily by controlling the field current, and it has a very high operating efficiency and constant speed. So, for operating speed less than about 500 rpm and for speed power requirement above 600 kilowatt, synchronous motor is cheaper than the induction motor, and in view of these advantages synchronous motor are preferred for driving the loads requiring high power at low speed. Typical example is reciprocating pump and compressor, crushers, rolling mill, pulp and grinders. Now, coming some the applications of these machines. So, it can be as a small rating machine, a small rating motor used for electric organ piano, then typically small synchronous motor used in automated typewriting machine, then a small rating typically 2.5 watt synchronous motor with step down gear from the microwave oven, then 120 volt synchronous motor used in microwave oven cooling fans and linear synchronous motors, then the synchronous motor positioning machines, then synchronous robot actuators, then hollow soft high speed spindle synchronous motor type, then clocks, record player turnables, then single pole synchronous motor with magnetized rotor, synchronous hysteresis motor, tape drive projectors, then air and gas compressors, then vacuum pumps, centrifugal fans, blower, compressor and exhausters, pulp and paper mills, ball mills, then roll of synchronous motor used in large water pump, then synchronous motor used in chippers and refiners in pulp production process, then large AC high speed synchronous motors, then synchronous motor for lifting application like gearless, and 3-phase medium voltage synchronous motor for offshore applications, and synchronous motor at centrifugal compressor in air separator, synchronous motors for crushing grinder and mills, and synchronous motor for crusher grinder and mills. Then ABB synchronous motor for pulp and paper applications are optimized for refinery and wood grinders and municipal clear water pumping facility. 6000 horsepower vertical synchronous motor variable frequency drive up to 450 rpm. Then pair of ancient carbon dioxide or air conditioning compressor powered by 2 antique 150 horsepower open frame synchronous motor. Then ball mill in mine ore process, that 500 horsepower to about 8000 horsepower synchronous motor, a synchronous speed of 120 maybe 120 to 400 rpm, and then high rating synchronous motor applications is reciprocating compressor, centrifugal compressor and pumps like, and the rating typically goes quite high, like in that case you can see the example typically goes from 5 megawatt to 100 megawatt. So, that is also typical size with variable frequency drive in 4 pole like. So, synchronous motors 164 rpm 3000 horsepower used in ball mill at an iron ore mine, then synchronous condenser installation, and synchronous motor used in mining, especially mine hoist, then synchronous motor used in hot strip mill to withstand severe environmental condition, then high speed blast furnace blower motor, synchronous motor, and synchronous motor for railway applications, then a Westinghouse bell type synchronous motor with DC excited motor typically in 1917, then synchronous motor used in electric vehicle applications, synchronous hysteresis motor type drive projectors, then rotor of synchronous motor used in large water pump, synchronous generator used in micro hydro for hydro power applications, then typically hydro generator with the rotor insertion. So, 3 Gorage Dam in China, that is 840 MVA 80 pole synchronous generator. Then you have another rotor generator with the again 3 gas 840, how it looks like from Assam. Then typically in Turkey 315 MVA 40 pole cylinder pole synchronous generator for hydropower, and synchronous generator used in diesel generator plant. Then synchronous generator 2 pole generator customized for the use of gas and steam turbine. Then synchronous generator 4 pole generator customized for use in nuclear power plant. Then synchronous machine as a condenser. So, now coming to the classification of synchronous motor. Now, the synchronous motor can be classified as wound field, permanent field and or reluctance type. So, we have a wound field, wound field means on the rotor we have a field winding of can be of both kind like cylinder pole and cylindrical. For low speed we use cylinder pole and high speed we use wound field. Then it can be brushless with the permanent excitation, and then we have a reluctance. Rotor on we have only the cylinder like. So, wound field synchronous motor has a distributed polyphase armature winding on the stator and DC excited field winding on the rotor, and the brushless construction is obtained when the rotor field excitation is provided by permanent, and synchronous reluctance motor uses an unexcited rotor having salient pole or projecting pole. And the typical example here is you can see synchronous motor, permanent motor and synchronous reluctance motor, 3 kind motor. So, this is synchronous reluctance motor recently have come from ABB and Siemens. They have become very popular because they are more efficient than index motor and more robust than your other synchronous motor, and this is with the typically with the permanent interior type of permanent motor for electric vehicle, and this is typically a conventional synchronous motor like. You can see that they are becoming synchronous motor day by day becoming popular for typically for majority of application, replacing many applications, especially for even a squirrel cage induction motor. So, the inverter construction is also possible, means field on the stator and armature on the rotor by principle, but the rotating armature system will require 4 slip rings including neutral connection, and the insulation rating will also be quite large. So, therefore, the rotating field system is preferred due to small DC excitation current and 2 slip ring. So, synchronous motor run at constant speed when fed from the constant voltage and frequency, constant frequency supply, especially conventional and wound field machines can operate at unity power factor at full load, and so minimize the stator current and inverter VA rating for the given shaft power. These machines can also operate at a leading power factor and thereby provide load compensation for the inverter, and the rotor of the wound rotor field motor may have salient pole or cylindrical construction depending upon the speed of the operation. So, now coming to classification of this synchronous motor, they are classified basically in 2 kinds as a synchronous motor and synchronous compensator. So, basically there are many classification of this synchronous machine or motor. In general, they are classified as synchronous generator or the synchronous machine driven by steam or hydraulic or diesel generator set and generate electricity, and synchronous motor are the machine which working to generate typically general power supply network at 50 Hz, 60 Hz or sometime at 25 Hz, and they are used in constant speed drive and compressor blower. And synchronous compressors are the synchronous motor running at leading power factor to supply reactive power to power system network. Now, coming to type of synchronous generator. In synchronous generator, DC excitation given to rotor field winding produces a magnetic field, and the rotor is also driven by external prime mover producing a rotary magnetic field which induces 3 phase voltage in the stator windings, and the classification of synchronous generator is on the basis of the type of prime mover and based on construction. So, coming to the classification of this synchronous generator, the type of prime mover, based on the type of prime mover used, synchronous generator are classified as hydro generator. These are the generator driven by hydraulic turbine, they run at low speed less than 100,000 rpm, and Francis turbine, Kaplan turbine and Pelton wheels are the most commonly used hydraulic turbine. And turbo generator, the generator that are driven by steam turbine are called turbo generator, and they run at very high speed above 1500 rpm, and engine driven generators. So, they are driven by various forms of internal combustion engine with a speed less than 1500 rpm, and these are the typically kind of, you can call it the type of synchronous generator. I mean diesel generator, then you have a typical thermal generator and hydro generator like. So, now coming to typically classification based on the construction, the most widely used synchronous machines have a stationary armature and rotating field system, and these synchronous machines are classified into 2 types in according to the construction of rotor. The salient pole machine, these type of machine have protruding poles with the concentrated winding as shown in the figure, and this construction is adopted only for slow speed or low speed machines, and it becomes very difficult to retain the salient pole against the large centrifugal forces developed. And non-salient or cylindrical rotor machines, and the field winding is not concentrated, but distributed in several slots which are milled over the rotor surface as shown in the figure. Since the poles are not projecting, this type of construction can be used for turbo generator which have a high rotating speed of 3000 rpm or 3600 rpm, depends on 50 Hz or 60 Hz supply. So, typical is your salient pole construction. So, we have a typically a armature winding on stator and field winding on the rotor, to which we give the through slip ring the DC excitation, and this is the typically the salient pole construction with the high number of poles. Practically this machine is with the high number of poles only, because it is used now hydro generator or we call it water wheel generator, which have a large number of poles. So, you have on rotor large number of poles, on which the field winding is put is wound here, and on the stator pole face we have a what we call it like a compensating winding or damper winding, we call it like okay, we put on the pole faces like also. So, this is cylindrical rotor machine. So, we have typically the cylindrical rotor and we put the winding only on 1/3 portion of one pole pitch, and normally they are of course 2 pole machines because they run at very high speed around 3000 to 3600 rpm. Now, coming to typically construction of synchronous machine. So, construction aspect of synchronous machine. For the construction of cylinder pole and cylindrical machines, the following parameters are of typically paramount importance: peripheral speed or centrifugal force, critical speed and runaway speed. So, this peripheral speed and centrifugal force, the peripheral speed of machine is given V equal to pi d n in meter per second, where d is the diameter of the rotor in meter and s is the speed in revolution per second. So, the volume d square L of the machine had to be increased if the power output have to be increased. However, it had to be noted that d cannot be increased to any extent. So, there is a restrictions imposed on the diameter d. So, for the 2 pole machine 50 Hz with the ns equal to 50 rps. So, d is 1.2 meter and V peripheral speed is 188 meter per second. So, this is the maximum possible peripheral speed and the corresponding centrifugal force is the maximum which a rotating mass can withstand. Now, the critical speed, that is in deflection in the rotor, that is delta m omega square eta k minus m omega square. So, at some angular velocity say omega c called critical speed, the denominator becomes 0 and hence the deflection becomes infinite, which is dangerous for the machine. So, designer must aim to make this machine to operate at a speed away from the critical speed as far as possible. So, now the third term is the runaway speed. When the full load is suddenly thrown off, the prime mover try to race as it will be receiving full supply of water or diesel or steam. So, this speed is called runaway speed. In water wheel generator, the speed governors are not quick acting like turbo generator. The runaway speed may be as high as 2.8 times the rated speed, causing the greater mechanical stress, and the machine must be designed to bear such great forces. And the maximum peripheral speed for which the cylinder pole machines is designed is generally 140 meter per second, while the turbo generators are designed for a maximum peripheral speed of 180 meter per second. Now, these are especially construction of hydro generators or water wheel generator, which are used in your hydro generating system, or you can call it in the dam, water dam. So, these are cylinder pole machines running at low speed. The construction is mainly based on the type of turbine and water head available. So, for a given frequency, a large number of poles are demanded at low speed. So, this type of machine will have large diameter. So, with diameter as large as 15 meter, it is just not possible to transport the machine in a single unit. So, therefore, it is designed to transport it to site in sections. The machine must be designed to withstand the centrifugal stress produced at twice of the normal operating speed as an convention, and this is the typically you can see the cylinder pole machine cell pole rotor looks for parts of the synchronous mode driven cylinder pole construction here. And this is the typically the stator core is made of laminations of low loss silicon steel, usually CRGO, cold rolled grain rotated steel, and core is supported by the tail by bars to the outer cylindrical frame. So, steel parts and the typically and its parts, and the stacked stator core cross section, as you can see the cross section of stator core. Then the typically the top view of one lamination sheet and single part stator lamination. Then welded stator housing of synchronous hydro generator, as you can see what is the side typically compared to the main side, and then you have assembling the laminations of stator frame to form the core. Then the pressing of laminated stator iron core with the hydraulic cylinders. Now, coming to stator winding, the 3-phase windings are placed inside the slots of laminated stator, and multi-turn coils are generally used, as you can see the stator winding inside the core slot. And here the construction is the big generators, only 1 ton per coil. The coil is split into 2 halves, 2 bars, and here it is visible. So, insulating 1 bar for a 2-pole turbine generator with a glass fiber and with a mica layer of the high voltage insulation. The insulation of high voltage stator winding with typically insulation powdered insulation robot, and this is typical resin impregnated coils are heated in the oven dry and harden the insulation. And then typically you can say how high voltage from wound stator coil with several turns NC for 2-layer winding, as you can see the diamond shape with the coil terminals and winding connections. Then you have a how it is the winding put in stator, winding is put in the slots of the core. Then you can see the winding high voltage stator winding of synchronous generator press, hydro pressing a winding parts in the slot. Now coming to construction of the rotor, so you can call it shell and poles are carried out on rotor body. So type of rotor construction largely depends on the peripheral speed, and rotor pole that are laminated are bolted on the rotor body for low peripheral speed of 25 meter per second. For high peripheral speed dovetail or T headed rotor is used. And how it look like practically the slots for the, you can call it the 4 damper bars in the rotor. So poles are built as laminated stacked to suppress eddy current and which are induced by slot triple magnetics air gap filled due to the stator slot opening. And now you can say rotor rim adjustment after stacking the laminations. Then the rotor assembly of the rotor parts, typically supporting parts. Then you can see the fixation of rotor poles for high centrifugal forces, and you can see the damper bars how they are placed in the typically in the rotor. And this is the typically you can call it the rotor winding. So winding coils, the rotor coils are framed from rectangular sections of strip to copper or aluminum and manufacture field winding of the shell and pole machines like. Now you can see how the 3-fold hammer fixed head fixation and cooling fins by increased copper width and damper rings segment like. So now the damper winding, these are employed to control the oscillations and hunting in the machine. They are copper bars placed on the slots in the pole shoe with the end connections attached to the poles, and they are used for providing the starting torque, especially in synchronous motor. As you can see the starting torque similar to induction motor. And this is typically how the now rotor look like. So the shell and pole rotor, so the 12 fixation rotor poles, completed big hydro shell and pole synchronous rotor for high centrifugal force at over speed of 14 pole, and then the complete assembled rotor, and then the segmental sleeve bearing for vertical load and dovetail bearing segment on vertical. So now for coming for the cooling, most hydro generators are air cooled for cost, simplicity and reliability reason, and fans placed on the rotor shaft are often used to circulate the air either in axial or radial direction, and the heat is mostly removed by air to water heat exchanger placed on the stator frame or close to the stator frame, and it is feasible to have the air circulating in a closed loop to minimize the risk of dirt exposure on the winding and air duct. Now construction of turbo generator, especially which are used in, it is also called steam generator. A 50 Hz turbo alternator is essentially a 2-pole machine at 3000 rpm, and diameter of the rotor is limited to 1.2 meter because of reasons stated earlier due to peripheral speed and centrifugal forces, and the machine has a high efficiency at high speed. To increase the rating, the axial length, electrical loading and the magnetic loading of these machines are exceptionally high. So this will increase the temperature of the machine, and so sophisticated cooling mechanism like hydrogen cooling or direct vortex cooling are to be adopted. So stator core built for segmental lamination, the slots, ventilation holes and dovetail keyholes are punched together for the purpose of cooling. And then you can see the typically the stator assembly of turbo generator stator stacking, as you can see. Then the 3-phase double layer and short pitch coil are used for are placed in the slot for typically in the stator winding. So now coming to the rotor, typically only 1/3, typical 2/3 portion of the slots are taken by the winding. So rotor of cylindrical made of solid forged of alloy steel. The surface is mild to form the slot, and normally about 2/3 of the surface is slotted and the rest is left unslotted, and typically concentric multi-turn coils are used. And you can see how the rotor look like here, the winding wound on the rotor of cylindrical synchronous machine used for turbo generator, and how the construction stacking of rotor with iron sheets and rotor slots for the field winding, and damper cage here, and with concentrated field coil. And then you can just see in the assembled distributor how is the typically field winding, then the damper winding, damper cage and rotary spider. Then coming to now construction of synchronous motor. Those synchronous motors have typically similar construction as that of synchronous generator, with the rotor construction mostly with the silent pole, which are run at low speed, but they are of course high speed synchronous motor which are of cylindrical nature. These motors are not self started, so they are started with the help of damper winding. Now coming to operating principle. So when the rotor is excited with the DC and rotated, the resultant field also rotates, so that the sinusoidal voltage are generated in the 3 phase displaced 120 in time and having a frequency directly related to rotor speed, as you can see here how it is rotating. And the elementary 3 phase 2 pole synchronous motor has a stator equipped with the 3 coil displaced 120 degree from each other, and those shown as a concentrated winding, they are usually distributed winding, as you can see here. And to understand the operation of synchronous machine, generator or motor operation, it is necessary to understand the production of stator field winding, special MF and the interaction with the field winding. So on the rotor you have field winding excited by DC, on stator you have a 3 phase winding distributed in 120 degree displace, and this is the typically you can call it the induced EMF voltage 3 phase at 120 degree phase or A phase, B phase or C phase. Normally we call it red, blue and yellow and blue. So coming to spectral MF distribution winding, so we have two windings, stator and rotor, stator 3 phase winding and rotor field winding. So most armature have distributed winding. So individual coils are connected so that the result is a magnetic field having the same number of poles as that of field winding. So magnetic field of the distributed winding can be approached by examining the magnetic field produced by the single end turn, which spans 180 degree electrical as on the typical side. So 180 degree, I mean we put the winding how it is shown the air gap produced by the current in this particular winding. So schematic view of the flux produced by a concentrated full pitch winding of a machine with the uniform air gap. And typically you can say the fundamental MMF, fundamental component of this quasi square wave distribution is given F A equal to 4 upon pi and by 2 I cos theta A, and fundamental component of air gap flux density uniform air gap is B 1 equal to mu 0 F A 1 upon G, and that comes like 4 pi mu 0 upon G and by 2 I cos theta A, where G is the air gap length. And from this the MF of one phase of distributed 2 pole 3 phase winding with full concentrated coil with the distributed winding, how it is the MF wave comes here with distributed winding of typically, I mean you have A phase, C phase and B phase, the distributed winding here, and how the MF comes from excitation of one winding. So upon component of this quasi square wave for MF multipole winding having n phase, 3 turns per phase given by F A 1 equal to 4 upon pi K W N P H by pi poles I cos theta, P poles by 2 theta A, where K is the K W is the winding factor, theta is the spectral angle, and stator electrical frequency F is given F equal to poles by 2 into n by 60, where n is the RPM speed. So MF wave of polyphase winding, as you can see here the 2 pole 3 phase typically stator winding, we have a phase, B phase and C phase, and how this is the induced voltage MF wave of a polyphase winding, you can say how it is typically going with respect to the time with the different magnitude, and as you can see here typically for A phase, B phase and C phase how they are placed for, and that represents the corresponding to kind of a combining together as a rotating magnetic field. So now under balance condition we can say instantaneous currents are 3 phase balance current I equal to I m cos omega t, I b equal to I m cos omega t minus 1 t, and I c equal to I m cos omega t plus 120. So MF for A phase have been shown F A equal to F A plus 1 F A minus 1, and you can say 4 pi by K W N P H P I A cos theta A, that is 4 pi K W N P H P I m cos theta I cos theta A E, and that becomes your half typically F m cos theta E minus omega t plus cos theta E omega t plus phi. Similarly, so these are for positive and forward, this is for typically the maximum value of F m 4 pi by K omega and P H I m by P, and the MF for B axis will be at minus 120 degree from A, and you can have for B phase similar excite typically the MF for forward and backward. Similarly, for C phase you have forward backward. Then when we combine together F A theta total MF contribution from all the 3 phases, that will be F A 1 plus F A B plus F A C, and when you and similarly you combine typically the backward. So, the sum of the backward will become 0, and for the positive travelling when we combine together, so it will become 3 by 2 f m cos theta a minus omega e t. So, thus the resultant displacing the 3 winding by 120 degree in the space phase and displacing the winding current by 120 degree in phase in a single positive travelling wave. So, air gap MMF wave described in equation is space fundamental sinusoidal function of electrical angle, that is space angle theta equal to by poles into theta e. It has a constant magnitude of 3 by 2 f m x. It has a positive peak at theta a equal to 2 by poles omega e t. Thus, under balanced 3 phase conditions, the 3 phase winding produces a air gap MMF wave which rotates at synchronous angular velocity omega s, and that is omega s equal to 2 by poles into omega e. So, omega is the angular frequency of applied electrical excitation in radian per second, and omega s is the synchronous spectral angular velocity of the air gap in of MMF wave. So, in general, a rotating field of constant amplitude will be produced by a q phase winding excited by balanced q phase currents of a frequency f e when respective phase are located 2 pi upon q electrical radians apart in space. So, amplitude of this flux wave will be q by 2 times the maximum contribution of any phase, one phase, and the synchronous angular velocity will remain omega s equal to 2 by pi into omega e radian per second. And this is the graphical analysis of the polyphase MMF wave. So, you can say at this particular time you have 3 by 2 here, and this is the contribution for all typically 3 phases. You have a phase, B phase and C phase, and resultant is this, and under this period after 60 degree you have a resultant f equal to 3 by 2 again maximum, and you have a typically the contribution of A phase, B phase and C phase. Similarly, for again for 120 degree you have again resultant will be f equal to 3 by 2 f m, and you have a contribution of A phase, B phase and C phase. So, that is the way how rotating magnetic field rotate, and this you have a good example how you are having a changing the excitation. Of course, rotating magnetic field is rotating, but the stator is not rotating like So, this is the kind of excitation you have for all 3 phases which get the resultant magnetic field. So, now coming to advantage of stationary armature and rotating field construction, which of course, partially we talk about. It has a increased armature tooth strength, reduced armature reactance, improved insulation, more rigid construction, and reduced number of insulators helping only 2 for DC, and reduced rotor weight and inertia and ventilation, and improved heat dissipation. Now, coming to the generation of induced EMF. So, we have a typically you can call it the here the magnet excited, we are putting the conductor here, basic concept. So, conductor L length moving in a magnetic field of B generate induced EMF, where phi is the flux, T the time in second, E is the average induced EMF in volts. So, instantaneous induced EMF is expressed E equal to B L U where volts, where U is the relative linear velocity between the conductor and the field like. So, we can say if air gap is uniform. So, we can call it B peak can be found out, B p equal to 4 mu 0 upon pi g into K f into a N f pole into I f, that is the field current, N f is the number of turns in the field winding, and you can call it like you can here a B will be our B peak. For cellular this will cos pole pi 2 theta r, that is the flux distribution as a sinusoidal in the air gap as a function of peak flux density, and phi p can be found out from the integral of flux density over the pole, phi p equal to L into minus pi by 2 poles to pi by 2 poles into B peak into cos p by 2 theta r theta r, and this will be 2 by p 2 b peak L r, where the r is the axial length, r is the radius, and theta is the measured angle like also. And you can find out typically the generated the lambda a equal to k omega n phi cos p by 2 omega t r, and that can be written k w n p h phi cos omega m e into t, where omega is p by 2 omega m. So, the mechanical rotor velocity expressed in electrical radius per second. So, according to Farrell induced voltage E equal to d lambda upon dt, that will become k w into n p h into d phi upon dt into cos omega m t. So, that becomes minus omega m e into k w n p h phi sin omega t, and the polarity of this induced voltage is such that if the stator coil were shorted, the induced voltage will cause a current to flow in the direction that will oppose any change in the flux linkage of stator coil. So, now you can just see here distributed magnetic field due to the 3 phase winding, how it is coming for typically at different instant of time when it is rotating from 0 to 30 degree and then 60 degree, and then how it is a rotating magnetic field, you can say when both rotor when the both rotor is excited and rotated and 3-phase induced EMF in a stator winding, and here is the magnetic field produced. So, this is the how you will get induced EMF in the stator when you give the field current to the your field winding and you have MMF, and then the flux phi f, and EABC and IIBC are the currents, and phi is the armature flux, and resultant flux is the sum of the field flux as well as armature reaction flux. And then here you can see how when the you are exciting the rotor with the DC, so you get the like a poles NS poles here 4 to pole, and then you have a induced EMF in armature conductor which is alternating current you can see here like Now, coming to equivalent circuit of this synchronous generator, the internal generated voltage produced in one phase of the synchronous generator is given as E equal to root 2 pi NC phi into F. However, this voltage EA is not usually the voltage that appears at the terminal of the generator. So, in fact, only the internal voltage EA is the same as that of output voltage V phi of the phase when there is no armature current flowing into the. So, this is you call it the induced voltage. So, why the output voltage is V phi from a phase is not equal to A, and what is the relationship between the two voltage. So, there are a number of factors that cause the difference between A and V phi. The distortion of air gap field produced by the current flowing in the stator called armature reaction, and the self inductance of the armature coil, the resistance of armature coil, and the effect of cylinder pole rotor shape like. So, the distortion of the air gap magnetic field by the current flowing in the stator called armature reaction. So, why no load on the generator, there is no armature current flow and A will be the equal to the V A, and rotating magnetic field produces the internal generator voltage E A here. And now, the distortion in the air gap field produced by the current flowing into the stator called armature reaction. The generator is connected to a lagging load, the peak current will occur at an angle behind the peak voltage. So, resulting voltage produce a lagging current from when connected to the typically lagging load. So, distortion of air gap field produced by a stator called armature reaction. So, the stator typically basically the magnetic field produced by due to the current in the stator winding. So, distortion in air gap field by the current flowing in the stator called. So, with the two winding present in the stator, the total weight in the phase is the sum of the internal voltage E A and armature reaction. So, V phi will be A plus E stator, that is corresponding to armature reaction. So, net field will be net be the sum of the two field, that is B net equal to B r plus B s. And since the angle E A and B r are the same, the angle of E stator and B s are, so resulting field B net will be coincide with the net voltage, and the voltage E state is directly proportional to the current. So, we can say armature reaction voltage can be expressed as E state equal to minus J x I A, and voltage in the phase will be then V equal to E A minus J x I A, and that is the equivalent circuit, that is the induced voltage in generator, and this is the reactance, we call it synchronous reactance, and then when the current is flowing and you are connecting the load here, because of which current is flowing like. So, now we can say in addition to armature reaction, the stator coil have a self inductance and resistance. So, total difference between A and phi will govern B phi equal to A minus J x I A minus J x A into I A minus R A I A. So, the armature reaction effect and the self inductance in the machine both are represented by reactances combining into single reactance called synchronous reactance of the machine. So, we can call it x s equal to x, this reactance plus x A, and then you can call it V phi will be equal to A m minus J x s into I a minus I a R a. So, you can call it like a typically this is field excitation, you are applying voltage and you can control the field current, and here you have a typically the you can call it the here the excitation voltage, reactance and resistance. Now, you can see the machine can be connected 3 phase either delta star or delta. Normally, delta is preferred for generator operation because you want to neutral to feed the single phase load. Now, coming to typically steady state power angle characteristic. So, we have here E f which we discussed, we have a resistance and we have a reactance, and this is the virtually you can call it the connected to the grid or the load. Normally, we connect to the grid. So, current I is flowing, and this is the typically the let us say voltage to which power we are feeding from the generator, maybe this voltage is of the grid voltage. Then we have a I, and let us say it has a lagging power factor current flowing. So, I R A drop I x, and this will become E f, that is the induced voltage. So, this we call it the phasor diagram of this cylindrical machine, because here we are not considering only one synchronous. So, power delivered through the impedance to load voltage will be P equal to V t into I cos phi, that is all per phase, similar to what we talked about earlier also. Phi is the phase angle between I and with respect to V t, and the phase current will be I will be F minus V t, of course, with the proper angle upon Z. If the phase voltage and impedance can be expressed in polar form, so equal to E f into J delta. So, V t equal to V. So, V t consider as a reference. So, Z is R plus J x, that is Z e to power J z. So, delta is the phase angle by which your E 1 leads V t, and phi z is tan inverse x upon R is the phase angle of the impedance. Then I will be equal to E to power J phi, that is E f e to power J delta minus V t upon, because V t as a reference Z into E Z delta, that is becomes E f upon Z e to power J delta minus phi z minus V t upon Z e to power minus J phi z. Taking the real part of the above equation, so we can say I cos phi will be E f upon Z cos delta minus phi z minus V t upon Z into cos phi z. So, from above equation and substituting in previous equation gave P 2 equal to E f V t upon Z cos delta minus phi z minus V t square R upon Z square, or P 2 equal to F V t upon Z sin delta plus phi z minus V t square V square R upon Z square. So, where alpha z is equal to 90 minus phi z, and that is tan inverse R upon x. So, similarly, power P 1 at the source end of the impedance can be expressed P 1 equal to E f V t z sin delta minus phi z plus E f square R upon Z square. So, hence frequently if resistance is neglected, we can call it P 1 equal to P 2 equal to E f V t upon x into sin delta. This is per phase power. If you are taking 3 phase power, you can consider 3 into here like. So, if delta is positive, E f leads V t and power flows from the E f to V t, and if delta is negative, V t leads E f and power flows from V t to E f, that is the case of the motor, this is case of generator. So, this is the typical case here, equivalent circuit representation of synchronous machine connected to external system. So, we have excitation voltage, that is typically you can call it generator with the synchronous reactance, and this we can call it Thevenin equivalent of the external circuit, maybe the grid and with the reactance, and here we have in voltage here, and in this case we can call it the power flow is from typically from here to here E f V t upon x plus x e q sin delta. When delta is positive, means this has a delta angle, it has a 0 angle, but if delta is negative, then it means power is flowing typically from this side to this side, typically working as a motor like. Now, coming to armature reaction, the field current, flux and field current induced voltage. So, this is flux versus field current, and this is induced voltage and field current. So, you have a saturation with the typically with the increased field current. Initially, you do not have a saturation because field excitation current is lower. So, magnetic iron saturate if the speed of the rotation is constant, and the induced voltage will be function of field current, and the voltage field current relation will be proportional to the flux field current relationship. So, if the armature current is 0, induced voltage equal to terminal voltage, and if armature current flows, the induced voltage is no longer equal to the major terminal voltage. The reason for difference between the induced voltage and terminal voltage are armature reaction, armature leakage reactance and armature resistance. So, coming to typically armature reaction is a reduction in the magnetic field density due to armature current creating a magnetic field that opposes to the main field, and consider the rotating magnetic field and a multi-coil stator winding. As the magnetic field rotates, the voltage induced in each of the coils in phase with the flux density, and the magnetic and electrical phasors are similar like. So, this is typical, you can see the how the field excitation comes there and how you will have a current and feel the field produce here like. So, now these are 3 phase current flowing. So, mathematically the net magnetic field is B net equal to B r plus B s, and the net voltage can be V equal to E minus I a x. If resistance is neglected, term I x is used to account the armature reaction. Finally, the terminal voltage will be equal to reduced to this V equal to J x a x into J I a x a minus I a r a, and the x s term is the synchronous reaction to include armature reaction and leakage reactance. This is equal to V plus I a r a plus J I a x s, and that we call it synchronous reactance. And this is the effect of armature current that supplying the typically a pure resistive load. So, you can just see here the how the effect of armature reaction, you are exciting the field, and this is the you can say field produced by the armature current, which really oppose on one side and which adds to the other side. So, this is the phasor diagram of the MMF diagram and voltage. So, this is terminal voltage at unity power factor, I r a drop, I x drop, the internal voltage, and this is armature reaction, and this is your typically the induced voltage. So, this represents the effect of armature reaction which are in typically at the quadrature with the voltage like, and this is with the effect of current when it supplies 0 power factor, that is lagging power factor. So, here you can see it is clearly opposing the field produced by the armature, it is clearly opposing the your excitation field like. So, consider this generator to be connected purely inductive load. So, current I A is the coil lags behind the induced EMF by 90 degree lagging corresponding to quadrature period in time. It is obvious that the impedance of hysteresis coil now direct opposition those of one on the pole, thereby reducing the total flux and induced EMF. So, since hysteresis and rotor ampere turns act the same direction, so there is no flux distortion, no torque, and hence the load rotates though additional mechanical power. So, this the field produced from the armature is just opposing exactly to the main fixed pole. This is typically the phasor diagram VIA, IRA, IXA, and this is the armature reaction, and you see here typically the induced voltage have to be higher to compensate the armature reaction like. And this is a case of your leading power factor. In case of leading power factor, it really produces the magnetizing effect of armature reaction. So, when generator is connected to purely capacitive load, the current I in coil leads to in by 90 degree. So, considering all such armature entity, the field EMF will be assisting to each other. So, that will really help to add the flux of the typically net flux in the air gap. So, that give you additing effect like, and here you can see when you have a VA, IRA, IXA, and you just see the induced voltage armature reaction is helping. So, EA is typically to be produced quite lower. So, armature reaction really help here to produce the, you can call it the helping the main flux poles like, as you can see here. I mean, it is adding the net flux is going to add here, and this is the phasor diagrams for different power factor. So, that is for lagging power factor. Here it is a demagnetizing effect of armature reaction, that is why induced voltage is higher than the terminal voltage, and here it is a little bit armature reaction effect on unity power factor, and here it is helping the armature reaction is helping to make typically magnetizing effect of, that is the reason E is I mean quite lower compared to what you have typically other two cases like. So, now coming to the numerical problems, a 4 pole a 2200 volt 3 phase star connected synchronous motor has a resistance of 0.22 ohm per phase and synchronous reactance of 2.4 ohm per phase. The motor is operating 0.6 power factor leading with the line current of 180 ampere. Determine the value of generator voltage. Phase voltage V equal to 2200 by root 3, that is 1270 volt. Resistance is 0.22 ohm. Here synchronous reactance is X equal to 2.4 ohm and power factor is 0.6 leading and current line current is 180 ampere. So, now generator induced EMF we have to calculate to cos 5.6. So, phi equal to cos inverse 0.6, that is 53.13 lead, and tan theta is x upon r, that is 2.4.22 10.91, and theta equal to 84.8 degree. So, phi plus theta plus phi is 53.13 plus 84.8 degree, that is 137.8, and cos theta plus that becomes cos 137.92, that is minus 0.7423. And now you can typically find out the synchronous impedance, that is Z s under root 0.22 square plus 2.4 square, that become 2.41 ohm per phase, and impedance drop now I z is 180 into 2.41, that is 433.8 volt, and generator induced EMF like now under root V square E square minus 2 V E r cos theta plus this, putting a value it comes 1618.3 volt, and hence the synchronous EMF will be root 3 times 1618, that 2803, and this is the typically phasor diagram. Typically here how it is the sum of the two drop plus this. So, you can have a drop, and this is the your next induced voltage. Now, coming to example third, a synchronous 3 phase synchronous motor is observed to have a terminal voltage of 460 volt line to line and a terminal current of 120 ampere at a power factor of 0.95 lagging. The field current under this operating condition is 47 ampere. The machine synchronous reactance is equal to 1.68, that is 0.78 per unit on a 460 volt 100 kVA 3 phase base, and assume the armature resistance negligible. Calculate the generator induced EMF EF in volt and magnitude of field to armature mutual inductance LF, and the electrical power input to the motor in kilowatt and horsepower. So, coming to the solution with the equivalent circuit here using the motor reference direction for current and neglecting the armature resistance. So, generator voltage can be find out equivalent to EF equal to VA into J XS IA. So, we can choose the terminal voltage as our phase reference. So, because of this line to neutral equivalent, the terminal voltage must be expressed in line to neutral. So, V A equal to 460 by root 3, that is 265.56 as a line to neutral voltage, and now lagging power factor of 0.95 leads to power factor angle. So, phi equal to cos inverse minus cos inverse 0.95, that is minus 18.2, I A equal to 120 at the angle of minus j 18.2. So, EF will 256 minus j 1.68 120 into j to power minus j 18.2 degree, that is 278.8 e to power minus 43.4 degree. Hence, the generator induced voltage equal to 278.8 volt RMS line to neutral. And the field to armature mutual inductance can be determined omega equal to 125. So, LF will be root 2 EF into I omega IF, that becomes root 2 279 divided by 120 pi into 47, that is 22.3 millihenry, and 3 phase input power will be 3 into single phase to power factor. So, 3 V I APF. So, 3 into 26.5 into 120 into 0.5, that is 90.8, that is 122 horsepower. Now, coming to example 4, a 200 kVA 480 50 hertz star connected synchronous generator with a rated field current of 5 ampere was tested, and the following data are taken. Vt at open circuit voltage at rated IF equal to 540 volt, rated source IL at short circuit at rated field current 300 ampere. When the DC voltage of 10 volt was applied to two terminals, a current of 25 ampere was measured. To find the value of armature resistance and the approximate synchronous reactance in ohm, that will be used to generator model at the rated condition. So, generator described above is a star connected. So, the direct current in resistance test give the two winding. Therefore, the resistance is 2 RA equal to VD upon IC. RA will be equal to VDC upon 2 IDC, that is 10 upon 2 into 25, that is 0.2 ohm. And generator voltage at the rated field current is given E equal to V1 Vt upon root 3, that is 540 by root 3, that is 311.8 volt. And the short circuit current IA is just equal to the line current. So, since that is I equal to ILS equal to 300 ampere. Therefore, synchronous reactance at the rated field current can be calculated RA under root RA square plus XA, that is E upon IA, and that is 0.2 square plus IXS square equal to 311.8 divided by 300, that is 1.039. So, that is squaring both, that will be 0.04 in plus XA square 1.08 and XA is equal to 1.02. Now, coming to another example, a 3 phase star connected round rotor synchronous generator rated at 10 kVA 230 volt has a synchronous reactance of 1.2 ohm per phase and armature resistance of 0.5 ohms per phase. Calculate the percent voltage regulation at full load of 0.8 lagging power factor. So, VO equal to under root Vt cos phi plus IR square plus Vt sin phi plus IXS square, as you see in the phasor diagram. So, just putting the value here of all. So, we get here V equal to 161.76, and then the voltage regulation VO minus Vt upon V, that is 161.76 minus 132.8 divided by 138 into 100, that is 21.8%. Now, coming to example 6, a certain 3 phase round rotor synchronous generator is rated 150 megawatt, 0.8 power factor, 12.6 kilovolt, 60 hertz and 1800 RPM, and each winding have a line to neutral resistance of 1.535 milli ohm. The data of no load magnetization characteristic is given in the table here. So, short circuit armature current test give a straight line through the origin and through the rated armature current of 700 ampere field current, determine the unsaturated impedance and determine the saturated impedance. So, it is the characteristic is given, your short circuit characteristic and open circuit characteristic are given here in terms of current and voltage and current. So, now drawing the phasor diagram to determine the voltage regulation. So, IA rated equal to 150 into 10 power 6 by 3 divided by 12.6 under root into 10 power 3 divided by into root 3 into 0.85. So, it comes 8086 ampere, and ZS saturated is 10.8 divided by root 3 divided by 4.6. So, it comes 0.979 ohms per phase, and your ZS saturated it comes 13.5 in pi divided by root 3 by 9.2, that is 0.847 ohms per phase, and phi is your cos inverse 0.85, that is minus 31.8 degree. So, now VO equal to the voltage calculated your typically comes like a your Vt plus the IZ drop, and calculating it comes like your 13281 at the angle of 30.4 degree volts, and regulation will be 13281 minus 7275 divided by 7275, that comes 82.6% like. and these are the unsolved problem which you can solve in the similar manner. These are the references which we have used to develop this material, and thank you very much.